When an aircraft enters zero visibility conditions, the pilot loses all visual reference to the horizon. Every input, every turn, and every altitude adjustment must rely entirely on the instruments inside the cockpit. Making that kind of blind flight possible requires an unseen electronic grid stretching across the sky. For decades, that grid has been generated by the VOR system, the Very High-Frequency Omnidirectional Radio Range. This chart details how physical VOR ground stations map out the specific corridors used to organize modern airspace. Those light blue Victor Airway lines connecting to the compass rose are the dedicated tracks pilots follow to navigate between stations. While GPS has become the primary navigation tool for modern aviation, VOR remains the mandatory redundancy. If satellite signals fail or are jammed, pilots must fall back on this ground-based network. It forms the basis for all instrument orientation training. The challenge is understanding exactly how an aircraft's receiver can capture invisible, omnidirectional radio waves and convert them into precise, absolute positional data on the instrument panel. Navigating by VOR requires a mastery of applied physics and spatial geometry, a technical baseline that remains a requirement for professional airmanship. To see how that positional data is generated, we have to look at the ground station itself. It transmits radio signals in all directions, but each specific direction carries its own unique electronic signature. This signature is created by broadcasting two distinct VHF signals. The first is the reference phase signal, which radiates outward as an omnidirectional wave, pulsing identically in all directions. The second is the variable phase signal. This acts like a lighthouse beam, rotating continuously at a highly precise rate of 1800 revolutions per minute. By comparing the phase difference between these two overlapping signals, the aircraft's receiver calculates its exact position relative to the station. As a baseline, when the aircraft is located exactly due north, at magnetic north, the receiver detects both the reference and the variable signals perfectly in phase. Their wave peaks align exactly. But as the aircraft moves to magnetic east, the physical rotation of that second signal introduces a mathematical delay. At exactly 90 degrees east, the receiver detects that the sine waves are precisely 90 degrees out of phase. These individual directional signals are defined as radials. You can picture them as absolute position lines projecting outward from the station, like spokes extending from the hub of a wheel. The system generates 360 distinct tracks, separated by single degrees. When operating normally, every single radial is transmitted to an accuracy within plus or minus 2 degrees. In real time, the VOR receiver solves this complex physics problem. It transforms the raw data into an absolute, reliable magnetic position line. This image displays the omni-bearing indicator. To decode those invisible radio waves into something a pilot can actually fly, the raw phase data has to be translated into this physical instrument on the panel. The interface begins with the Omni-Bearing Selector, or OBS knob. The pilot turns this knob to rotate the course card, dialing in the specific radial they intend to fly. Once a course is selected, the course deviation indicator, the vertical needle in the center, provides a mechanical line showing the aircraft's horizontal displacement from that exact radial. There is a critical law of VOR navigation at play here. The CDI does not show a fixed linear distance in feet or miles. It displays angular deviation from the station. Look at the deviation scale on the instrument face. Each horizontal dot extending out from the center circle represents exactly 2 degrees of course error. If the needle hits full-scale deflection at the 5th dot, it indicates the aircraft is off course by 10 degrees or more. Because the deviation is angular, it creates a funneling effect. At 30 nautical miles from the ground station, a 1-dot error on the instrument equals a physical offset of 1 nautical mile. But the physical distance off course widens the further away you get. At 60 nautical miles out, that exact same 1-dot deviation equals a physical offset of 2 nautical miles. This geometric relationship perfectly mirrors the aviation 1 in 60 rule that pilots use for mental navigation math. The instrument acts as an angular geometry translator, converting complex phase angle math into a simple visual interface. If the needle doesn't account for heading, how does the pilot know if following the selected course will take them toward the station or further away from it? The mechanical solution to this directional ambiguity is the to/from flag located right on the instrument face. The logic is straightforward. If the aircraft is physically positioned on the 090 radial and the pilot selects 090 on the dial, the flag will read from. Flying a heading of 090 will take the aircraft away from the station. Conversely, if you leave the plane in the exact same physical spot but dial the reciprocal course of 270, the flag mechanically flips to 2. The to/from logic separates the concept of heading from position, allowing pilots to orient themselves in space without directional confusion. Even with the to/from flag, the standard display has a human factors flaw. If a pilot flies a reciprocal heading opposite to their selected course, the instrument suffers from reverse sensing. In a reverse sensing scenario, the needle deflects in the opposite direction of the desired track. The pilot is forced to manually reverse their physical control inputs, steering away from the needle to center it, which induces intense cognitive load. This diagram illustrates the Horizontal Situation Indicator, or HSI. It is a mechanical evolution explicitly built to eliminate reverse sensing. The HSI integrates two functions. It takes the VOR deviation needle and superimposes it directly on top of a remote indicating compass card. Because the compass card automatically rotates as the aircraft turns, it constantly aligns the entire VOR display with the aircraft's actual magnetic heading. Look at the inbound tracking maneuver shown here. As the aircraft turns toward the station, the instrument physically maps the selected course relative to the miniature aircraft icon in the center. The needle stays on the correct physical side of the aircraft. Thanks to this automatic rotating link, the needle always points toward the selected course line. There is never reverse sensing on an HSI. It completes the evolution of radio navigation in the cockpit, turning a static mathematical readout into a dynamic command instrument that aligns with the pilot's perspective. The entire VOR architecture is an exercise in applied physics. A ground station sweeps a variable phase wave, a receiver calculates the angular offset, and an HSI commands the spatial geometry to the pilot. Because IFR flight stakes lives on the accuracy of this invisible grid, the FAA requires rigorous, logged operational checks of the receiver before entering the clouds. This sectional chart notes the Greene County MORTAC. Pilots use certified test signals or dedicated ground checkpoints like this to ensure the receiver's phase interpretation remains accurate within a strict tolerance of plus or minus 4 degrees. You must also tune the frequency and listen for the precise Morse code identifier. Until that code is positively identified and the off flag disappears from the display, the instrument's geometric output cannot be used. Satellite architectures represent the future of navigation, but the ability to translate phase physics into precise movement remains a required skill for any instrument-rated pilot.